Hello and welcome to this presentation related to our Applied Maths unit. In this session we reviewed the past paper from June 2017. Here's an overview of the paper's contents. As with our previous presentation related to the sample paper, I'm simply going to state the problem and the solution to each of the 7 questions on the paper. In our revision session 2, we worked through question 1 and question 2 in detail, and I outlined question 4, showing the various steps involved, and I left question 5 and question 7 for you to undertake for enrichment. Briefly overviewing the respective problems. In question 1, we had a short proof to derive, and we had to calculate the area, volume and the mass of a steel bush. In question 2, there's an electrical circuit context. From the question, we had to generate 2 simultaneous equations and then solve them using matrices. Question 3 relates to a hydraulic jack context. This essentially involves generation, transposition and evaluation of various equations associated with the movement and the forces involved within the jack. Question 4 I did outline to you. It's an integration application and it relates to calculating the centroid of an area. In other words, calculating the x and y bar locations for the area. Question 5 involves exponential functions, solving for stated parameters, and we also have to undertake differentiation, which includes using the product rule, so a non-standard differential. Question 6 relates to an energy balance. The context here is a wheel rolling down a slope. Got to generate a proof, and it involves solution of various equations. And question 7 is essentially a first order differential equation of the form dy by dx is equal to a function of y. So the rest of the presentation very briefly shows the respective question and the associated solution. Again, I've tried to label the solutions to show all the steps involved, so hopefully make it easier to follow the process involved in developing these solutions. For your reference, here are the approximate start times related to the 7 questions shown within the presentation, should you want to directly review a solution to a specific question. Please note that generally all times are rounded to the nearest minute. So here's question 1. Essentially you have to derive this equation here. There are some hints shown on the following slide. Question 1 continued. Here are some hints related to the formula sheet provided by the awarding body that can be used in the assessment. We essentially have to find the formula for the area of the segment, shown here, the formula we're trying to prove. So question 1 part A, here's the solution related to the proof. I'll let you review all the solutions at your own pace. Question 1 part B, item 1. Let you read this at your own pace. The full work solution is shown on the following slides. And essentially we're asked to calculate the surface area of the face of the bush, shown cross-hatched on this pictorial representation. Question 1, part B, item 1, continued. This shows the breakdown in calculating the surface area of the bush shown. We calculate area 1, which is the annulus of the face of the bush. We need to then subtract from that a rectangular section, and also using the formula derived on the previous slide, subtract the area of a segment. Question 1, part B, item 1. Here's the full work solution for you to review at your own pace. Question 1, item B, part 2. We're going to calculate the volume of the bush. We're given the thickness of the bush in the question. That's a fairly straightforward solution to find the volume in millimeters cubed here. Question 1, part B, item 3. Got to calculate the mass of the bush. We're given the density of the material in the question. Notice I convert my millimeters cubed to meters cubed using a unity bracket. Here's my unity bracket shown here. There's a separate presentation related to unity brackets if you want further information. And here's the calculation of the mass in terms of kilograms, but final answer stated in grams. This question 2 relates to our electrical circuit shown here. in figure 4. Give us some information in the question related to resistances and currents. Question 2 continued. Part 1 here, using the values in the equations shown above, we've got to show that V1 and V2 satisfy these two equations. Question 2, item 1 continued. Here is a hint how to commence a question. I'll show you the full work solution on the following slides. So question 2, item 1, here's the solution to generate the first equation shown here. Just notice in this line here I multiplied throughout by 108. This allowed me to remove the fractions in the above line. 12 times 9 of course is 108. So as I say, so it's just a method of actually removing the fractions. And here's the second part of the solution to generate the second equation given. And question 2, part 1 continued. This is purely an alternative solution using fractions. So you can see here, instead of multiplying throughout by 108, I've actually placed the V1 and V2 in terms of fractions. Obviously the same answer is produced. And again, using my fractions here, same answer is produced as in the previous method. Just a very subtle difference in these solutions, that's all. Question 2, part 2 continued. We've now got to express these simultaneous equations in matrix notation. I'll show you the full work solution on the following slides. Question 2, part 2. Here's the solution using matrices. I'm going to let you review this at your own pace. We reviewed matrices in our previous lecture related to the sample paper. And question 2, part 3. Using matrix algebra, we're asked to calculate the values on V1 and V2. Question 2, part 3. Here's the full work solution. Here's question 3. This relates to the simple hydraulic lifting mechanism, the hydraulic jack. I'll let you review the question at your own pace. Question 3, item 1. Let you review the solution at your own pace. Question 3, item 2. We're given an equation. Essentially, we'll have to rearrange. Calculate F1. Full work solution shown on the following slide. Question 3, part 2 solution. Let you review at your own pace. Course given here. Question 3 continued. This is part 3. You read the question at your own pace. Essentially, we have to calculate the height gained, labelled as delta H, by piston P2 and its load. Piston P2 shown here, and here's its load. Question 3 continued. Part 3 solution. Let you review this at your own pace. Here's the value of height H calculated. Solutions continued on the next slide. In question 3, solution continued. Here's the value of delta H calculated. Note we're referring to the solution from part 1 shown here. Here's question 4. It relates to finding the centroid area under this curve here, function of x. We've got to calculate the x bar and y bar locations, and we're given a formula for x bar, integral of xy respect to x between our limits a and b, divided by the integral of y respect to x between our limits. So it's actually the first area moment about the y-axis divided by the cross-sectional area of the section. So the integral in the denominator is actually finding the area under the curve. And again, to find the y bar, we're given a formula. We find the integral of a half y squared with respect to x between our limits again, a and b. And again, that's all divided by the area under the curve. Four-word solution shown on the following slides. So question 4, part 1, calculate the area, this metal plate, the area under the curve. Solution shown on the following slide. Notice that y is equal to x squared plus 1. That's the equation of the curve shown here. Question 4, solution part 1. Here's the calculation of the area A. Here's our y function, standard integral, ax to the n format. Question 4, part 2. We have to calculate the x bar location, shown here. Here's the formula for x bar. Note we've already calculated the denominator, that relates to the area of the curve. What we need to do now is to calculate what's called the first area moment, that's the numerator. And we need to replace the y term in this integral with y is equal to x squared plus 1. That's the equation of the line. The full work solution is shown on the following slide. Question 4, part 2. Calculate the x bar. So initially we will calculate the first area moment about the y-axis given the standard formula. Place y here with our x squared plus 1 from the previous slide. And we determine the first area moment, from which we can then calculate the x bar, which is the first area moment divided by the area under the curve. And question 4, part 3, we now calculate the y bar location, shown here on the diagram. And again, as before, we've already calculated the area in part 1, and the numerator is the first area moment here. And again, we have to replace the y in this integral with x squared plus 1, so our equation. The full work solution is shown on the following slide. Question 4, part 3. So calculation for y bar. Again, we calculate the first area moment, this time about the x-axis, and then calculate the y bar. Here's the first area moment calculated, and here's the y bar calculated. Question 5 stated that for this question we should use the following result, given y is equal to e to the negative x divided by a all squared. The first differential is of the form shown here, so we can assume this in our calculations. And we're given an equation for our ski slope, context of the question here, shown here. It's an exponential form. In part 1 we're asked to sketch a graph of h against x, so h on the vertical axis, x on the horizontal axis, between our range shown here. Sketch shown on the following slide. Question 5, part 1. Here's the sketch of the curve. Our calculations shown for reference. Question 5, solution continued. Part 2, we've got to now calculate the value of x when h is equal to 15. So essentially we're given h here, and we've got to rearrange the equation to find x. Solution shown on the following slide. Question 5, solution continued. Part 2 here. So we're given h, need to find x, and here's the value of x calculated. Let you review the solution at your own pace. For question 5, solution continued. This is part 3. Now here we have to calculate the height of the slope at the point where the gradient is a maximum. So we need to read the question carefully here. We need to use this standard form shown in the question, given the function of y in this format. The first order differential equation dy by dx is in this format. Now to solve this problem, we will need to differentiate the height equation, shown here, with respect to x to find dh by dx, and that will be the equation of the gradient. But we will then need to differentiate it again because we want to find where the gradient is a maximum. So we'll need to find the d2h by dx squared, and we will need to equate that to 0 and solve for the value of x at which the gradient is a maximum. So we need to be careful how you read the question here. It's the gradient that we're trying to find as a maximum. The original equation relates to the height. It's not the height that's a maximum. We know that's a maximum when x is equal to 0, it's 30 meters high. We're trying to find where the maximum gradient occurs. So be careful that it's very easy to miss that point. And if you're struggling with this particular question, well, then you're not alone, because I found this a very difficult question to solve. Question 5 continued, here's part 3. So here's the full work solution. So we'll be using our standard form here. So given our function in this form, shown here for h, we'll be using our standard form, shown here, to find a solution for dh by dx, shown here. Notice that the 30, of course, is an additional value to the standard form. That's the equation for the gradient. Now we need to differentiate that again and equate the second differential to 0 to find the value of x at which the gradient will be a maximum. Here's the full solution to find dh by dx. And question 5, solution continued. We're now going to apply the product rule to find d2h by dx squared, because the dh by dx equation is a function of x here multiplied by the exponential, which is a function of x also. So as I said, we're essentially using the product rule here. And for your reference, here's an extract from the formula sheet that outlines the product rule, which we use to differentiate the product of two functions. Both functions u and v shown here are functions of x. I'll let you review the solution at your own pace. It's continued below. Here's the value of x calculated, at which the gradient is a maximum. When we square root a number, of course there is a positive and negative solution. I'm only considering the positive here. And then knowing the value of x, we can determine the value of h, at where the gradient is a maximum. This question 6 relates to an energy balance. I'll let you review this question at your own pace. It's basically a circular object moving down an inclined plane. Question 6, you have to prove this expression for the velocity. This is when the object has travelled 20 meters down the slope. Full solution shown on the following slides. Question 6, here's the commencement of the solution. It's continued on the following slide. Question 6, part 1, here's our energy balance. We commence from the initial energy at the top of the incline, which is potential energy. That equates to the final energy at the bottom of the incline, which will be in two forms of kinetic energy. So potential on the left hand side, we have linear kinetic and rotational or angular kinetic at the bottom of the incline, assuming no frictional losses. I'll let you review the solution at your own pace. It's continued below. Here's the expression we have to prove for velocity. Question 6, part 2. Let me read the question at your own pace. Notice we have to use the expression for v in part 1 here. Question 6, part 2. Here's your solution. Again, let you review this at your own pace. Essentially, we have to calculate the time it takes for the objects to travel a distance of 20 meters down the incline. Here's the time for the solid disk, time for the sphere. Finally, here's question 7. This is essentially a first order differential equation of the dy by dx equals a function of y format. Given in the question, standard integral, and the solution. An electrical context again here. Here's the differential equation given to us. We have to rearrange it to have the t term on one side of the equation, v on the other. The full work solution is shown on the following slide. So question 7, here's the full work solution using the above standard form. I'll let you review the solution at your own pace. Here's our final answer. So that's the end of the presentation, which I hope has been of some use to you, and I wish you well in the final examination.